Okay, record. Nur Ain baru masuk. Nur Ain.
Ya, saya.
Ke mana lambat?
Sorry, sir.
Ke mana
Sorry,
lambat?
sir.
Saya panggil daripada tadi lagi.
Sorry, sir. Sorry, sir.
Okay. Okay. Saya dah record. So today is 26 hari bulan November 2020 pukul 9.16 malam, right? So this is basically ganti yang plus hari Isnin, right? Isnin dan Selasa, right? Kita buat. Okay. So today I'm going to before I start the lecture for tonight, I'd like to ask you with regards to the lecture last week on the capacitor and inductor. Any problem? Any question? The assignment that I gave. Do you think that you can do those assignments? Boleh buat?
Boleh buat saya, tapi ada soalan tu confusing sikit, kena tengok balik recording lepas tu.
Okay. So nanti apa ni dalam minggu depan ke kita buat apa ni lah, the revision for the test, right? So basically that for the test starting from the first lecture until today's lecture, right? Until the transient analysis, right?
Okay, sir.
Okay. So now I'm going to share the slides. I have 39 slides for tonight. And we'll try to finished within these 2 hours. If not, we go to about 2.5 hours, something like that. Let me wear my Michael Jackson glove. Sekejap. And sambung saya punya tablet, graphic tablets, so that I can write. Okay. Okay. Let me share the application. So share. Can you see the slides?
Yes, sir.
Okay.
Yes, sir.
So this is the lecture on transient analysis, right? So this is the 5th, chapter, but in the textbook, most probably that is a different chapter number, eh? Okay, what is transient analysis? Transient analysis is basically that the analysis that you do to describe the behavior of a voltage or current during the transition between 2 distinct steady state condition. Basically that you have initial steady states and the final steady state. So in this case, for example, right? For example, so this is actually the initial steady state where it starts. This actually the initial steady state where it starts to change, and this is the final steady state. So the transient analysis is basically that the analysis of the behavior of the currents or voltage from the initial state to become the final state. So in this case, maybe it's in the exponential, this curve. or some of them can be something like this. So we are trying to analyze the behavior between this and the final state. So that is what we call a transient analysis. The behavior. So in this case, a steady state region for 0 to t, for a region between, for t between 0 to 0.2 seconds. So basically from 0 to 0.2 is here, or from 0 to 0.2. So this is the first steady state. Okay. And a new steady state region for t greater than 2. So basically that the new steady state is here, starting from t equal to 2 seconds, or from here, basically t equal to 2 seconds, where the voltage reaches a steady DC or AC condition. So the top one is the DC, the second one is the AC. So AC, basically you have this sine wave. This is the AC signal, right? So this is the DC signal, is just a single line, right? So that is the meaning of transient analysis. Normally that this transient analysis you do in a circuit where you have inductor and capacitor. Inductor or capacitor. Right? So regardless of how many resistors the circuit contain, it is a first order circuit. It called a first order circuit. The response of a first order circuit to a switch DC source will appear in one of the two forms shown
So
below.
your internet is problem, sir.
Hello?
Hello, sir. Your line is slow, sir.
Yes, sir.
Dengar tak saya punya ni?
Dengar, sir.
Dengar sir.
Light boleh
Baru
nampak
dengar,
tak?
sir. Okay.
Dia sedikit dekat.
Dengar, sir.
Sir, line slow, sir.
Line slow. Siapa yang ada masalah untuk nampak saya punya slide? How many?
Slide okay, sir.
Okay.
Slide okey sir, suara je.
Okay, sir.
Suara okay?
Suara okey, sir.
Dah okey sir. Sekarang okey sir.
Okay. So now I'm actually on the slide where you have one circuit up and two up at the top. You can see? Start with the regardless of how many resistors the circuits contain.
Yes sir.
Okay. So basically that a first order circuit will have the characteristic shown in the waveform below. Whether it's decaying or rising exponential responses. Right? So that is the response of a first order circuit. First order circuit is basically that you have either one inductor or one capacitor. You don't have both. If you have both, then it can be it will be a second order or higher. So the first order circuit is that you have only one capacitor or one inductor, right? So basically you have RL or RC combination, right? So let's say you have the circuits. You have one voltage source, you have one resistor and one capacitor. So now you want to write an equation for an RC circuit. So the circuits on the right is called a RC circuit, which is a resistor and capacitor circuits. So from here, you can write the KVL equation. Yeah, basically, it's a KVL. You nampak tak? Saya draw the loop, the arrow.
Nampak sir.
Yeah.
Okay. So basically that if you write the KVL, we have Vs. Vs is the current going out. Vs of t into resistor R. So minus VR of t and minus Vc of t equal to 0. Okay. Then from what we have learned, Vs is basically that VR is equal to R times IR of t. Okay. V equal to IR. Remember the Ohm's law? Okay. And you have R IRT plus Vc of t equal to Vs of t. Basically this one, you move to the side. Okay. So basically this. And you observe that IR and IC is the same because it's in only one loop here. So the current through the resistor is the same as the current through the capacitor. So IR is equal to IC. And this from last week, we learned that IC is equal to C dV over dt. Remember this formula from last week?
Yes, sir. Yes, sir.
Yes, sir.
So you can substitute the IR and IC with this equation. So you have R times T dVct over dt plus Vct equal to Vs of t. Or you can rearrange the equation, you get dVc of t dt plus 1 over Rc Vc of t equal to 1 over Rc of Vs t. So you have this. So this is actually a differential equation for these circuits. Okay? Simple. So from the KCL, we can derive the differential equation for RC circuits. Example, write the equation for these circuits. How do you want to write this? What are you going to use? KVL, KCL,
KVL.
KVL,
I think
KVL.
or KCL? Which one is easier?
KVL.
Note is what?
KVL.
KCL or KVL? Nodal analysis.
KCL.
KCL. So this one you use the KCL. What it says that the summation of a current at a node is equal to 0. So you have I going in, you have IL going out of this node and IR going out of that node. So you have IS going in node minus IR minus IL is equal to 0. So this is actually KCL. For the this one is KVL. KVL, this one. Right? So this one is KCL. Right? So IS minus IR minus IL equal to 0. So IR of t plus IL of t equal to IS of t. So what is IR of t? I is equal to V over R. So therefore I of t is equal to V of t over R. So basically voltage across here. So this is V of t. The voltage across the resistor divided by R is equal to I R of t. Okay. And plus IL of t plus IS, which is the source, IS of t. And from last week, the voltage across the inductor is written as L times DIL t over dt. And the voltage across L here is actually the same as VT here, or the voltage across the resistor here. So VT is equal to VL equal to L DIL dt over dt. Therefore, you can substitute this into the formula. So you have L over R DILT over dt plus ILT equal to IS of t. So this is the differential equation for RL circuits. So now you have, this is the differential equation for RL circuit, and this one is the equation for RC circuits. Okay. Yeah. So that is the how you derive the differential equation for RL and RC circuits. Any questions so far?
No, sir.
Tak ada. Okay.
Tak ada, sir, tak ada.
So any
No, sir.
circuit containing a single storage element, so basically is whether you have one inductor or you have one capacitor, right? Can be described by a differential equation of this form: A1 dxt over dt plus A0 xt equal to B0 f of t, or A1 over A0 dxt over dt plus x of t equal to B0 over A0 f of t, where x represent the capacitor voltage or the inductor current. So basically that if you have a circuit with a capacitor, then it's a voltage. If it's inductor, then it's a current in the circuit. So here, right? So basically that if a capacitor, then you have A1 over A0, okay? V of C, dVC dt, okay? Plus Vc of t equal to B0 over A0 f of t. So this is if capacitor. If it's inductor, then A1 over A0 d IL t dt plus ILT equal to B0 over A0 f of t. So I punya ni problem ni nak kena tukar, kena beli baru. Asyik jadi lain-lain. Okay. So that is the derivation of the what we call it differential equation for the RL circuit and RC circuits. Now we look at the DC steady state solution for initial and final condition. Okay. The terms DC steady state refers to the circuit that have been connected to a DC source for a very long time. So that is what we call a DC state. When it's connected to a DC, whether it's voltage or current source, for a very long time, such that it is reasonable to assume that all voltages and currents of the circuit have become constant. Okay? So that is the meaning of DC steady state. So the steady state solution is determined by the constant Ks, which is called the DC gain of the circuit. So basically that at the DC steady state, you have a you can assume that that circuit has a constant current or constant voltage. So And also at DC steady state, all capacitors behave as open circuits and inductor as short circuits. Okay. So this you must remember. It's very important when you want to do the circuit analysis. When you want to do this initial and final condition for DC steady state. This is very important for you to remember. The behavior of the capacitor and the behavior of inductor. So this is the equation that you have to remember. The currents in the what do you call it capacitor is equal to C dVc dt. So the steady state, the ICT of t is approaching 0 as t approaching infinity. And for the inductor, VLT equal to DILT dt. So the steady state, when the steady state at t approaching infinity, so VL of t approaching 0. So you have to remember this. Okay. This formula you need to remember also. Right. So the DC state, the DC steady state condition is usually encountered in two cases. Basically, the first case is the initial condition, and second case is the final condition. Initial condition means that at t equal to 0. And final condition when t is approaching infinity. So you have x of 0 and x of infinity. So this is actually your two DC steady state condition. So initial condition, basically that before a switch is first activated. So basically that you have a switch. So you have a switch. Okay. So initial condition is basically just before you close off the switch or you open the switch. So in this case, before you close the switch. So basically that if t equal to 0 is closing the switch, therefore the initial condition is just before. So we call it t equal to 0 minus. Yeah, we put this. Just before basically is x of 0 minus. So this means that just before t equal to 0, just before the switch is closed or open. And x 0 plus is basically just after t equal to 0. Just after. So in this initial condition for x equal to 0, x or at t equal to 0, then you have these two, x0 minus and x0 plus. For final condition, where x of t equal to infinity is a long time after a switch has been activated. So, for example, katalah asalnya switch is open, then you close. Then you have the circuit like this. So the final condition is actually at t approaching infinity. And note, capacitor voltages and inductor currents cannot change instantaneously. An instantaneous change in either of these variables would require an infinite amount of power. So basically that from 0 minus, from the condition at t equal to 0 minus, it cannot change to a different value when t equal to 0 plus. So this actually must be equal. So the value of an inductor current or a capacitor voltage just before the switch has been closed or open is equal to the value just after the switch has been closed or open. So basically, these two conditions, right? For a capacitor, the voltage of a capacitor just after the switch is closed or after the switch is on is equal to the voltage of capacitor just before, zero minus, just before the switch is closed or switch is on. Whereas for the inductor is the current, right? So you have to remember these two conditions, right? Example, let's say you are given these circuits, okay? Determine the initial and final condition of the switch shown below, okay? So initial condition, basically that you have this switch is at the position number 1, right? Then at t equal to 0, the switch is thrown to the position number 2. So now you want to do the analysis to find the initial condition and final condition of the circuits. And you are given the VS1 as 13 volts. Here is 13 volts. The inductor is 170 millihenry. R2 here is 4.3K. VS2 is 13 volt also. R1 is 2.7. R3 is 29K. So you are given this. So how are you going to do this first? First, basically that you need to find the initial condition. Initial condition, what is the current through the inductor? And for the final condition, you need to find the current also through the inductor. How are you going to do this? First, you have to draw the circuit. Okay. So you need to find the initial condition t less than 0. So at t less equal to 0, so this is the circuits. So basically that you have the loop here. Over here you don't have because it's disconnected. This disconnect from the source here. So there is nothing and no current is flowing there. So in this case, you have one loop. So you can write the KVL for this loop. So you are using the loop analysis. So the circuits in a steady state condition, the inductor behave as a short circuit. So this is the circuits when you redraw. So L is a short circuit. Now we can write the KVL. So we have VS1. Let's say we use the what do you call it, the convention, minus is going out. So minus VS1 plus the voltage across R1, which is R1 IL0, because this is actually the initial condition at I equal to 0, or 0 minus. This is actually at 0 minus, plus R2, the voltage across R2, which is R2IL, or at 0, plus VS2 equal to 0. So therefore, this one you can what do you call it, simplify the equation. So you get R1 plus R2 times IL0 equal to VS2, VS1 minus VS2. So you plug in the value. So 2.7 plus 4.3K times IL0 is equal to 13 minus 13. Because VS1 is 13 volt, VS2 is 13 volt. So 13 minus 13, so equal to 0. So IL 0 is equal to 0 because 0 divided by anything is 0. So this is the initial condition at time equal to 0. So you get one value. Second, you need to find the value for the final condition when you throw the switch to the second position, when you throw to this position, when you throw the switch there. So basically that you need to find at t equal to 0 minus 0 plus and t equal to infinity. What is the value for t equal to 0 plus? Remember the condition? The current in the inductor cannot change instantaneously. So IL0 minus IL0 plus is equal to IL0 minus equal to 0 milliamp for this one. Okay. So for final condition, when you have these circuits, now the switch is thrown to the second position and it's been long time like that. So you find the final condition for t approaching infinity. So after the switch has changed for a long time, the circuit again at a steady state condition and the inductor behaves as a short circuit. Thus, you have the loop here. You don't have the loop here anymore because there is no more current flowing. So you have a loop here. Then you can write the KVL. So what is the KVL here? You have the current, the voltage Vs2, the voltage across the R2, and the voltage across R3 equal to 0. So if you use the convention of current going out from the plus terminal is minus, then you get minus Vs2 plus R2 IL at the infinity plus R3 times RL IL at the infinity is equal to 0. So R2 plus R3 IL infinity is equal to Vs2. Okay. So IL is equal to Vs2 is 13 volts divided by R2 is 4.3 kilo plus 29 kilo. So it's equal to 0.39 milliamps. So itu 2 point berapa tadi 29 kilo. Okay. So R3 is 29 kilo, R is 4.3 kilo. So you have 0.39 milliamps. So there is another initial, this is another solution because you need to find the initial condition and final condition. So in the test, it will be something like this. Okay?
Okay, sir.
Can you hear me?
Yes, sir.
Okay.
Yes, sir. Yes, sir.
Okay.
Yes, sir.
So that is the example for the initial condition. So transient response of first order circuits. Okay. First order circuits basically that you have RC circuit and RL circuit or RL circuit. So first order circuit is any circuit containing one energy storage element, either an inductor or a capacitor, and a combination of voltage or current source and resistors. Resistors can be many. The voltage source or current source can be many. But the only component, the storage component that you have in the first order circuit is only one. It's either a capacitor or an inductor. Itu. So a first order circuits is characterized by a first order differential equation, just what we have seen before. So this equation. So to find the solution, basically that you need to find the A1, A0, B0, and A0 in this equation. So the general form of the first order system equation basically that you have A1 over A naught dxt over dt plus xt equal to B naught over A naught f of t. This can also be written as tau dx of t over dt plus x of t plus ks times f of t, where tau is A1 over A naught and ks is B naught over A naught. B naught over A naught is basically the gain. That's the gain of the circuit, the DC gain. Tau is the
Sir, I think you are lagging, sir. Can't hear just now.
time constant.
Sir, your voice sekat-sekat, sir.
Can you hear me? Sekat.
I can't hear you. Yeah.
Lekat-lekat, sir.
Boleh dengar sekarang? Clear?
Clear, sir.
Now clear, sir.
Clear.
So basically that tau is the time constant. Can you see the slides?
Yes, sir.
Okay.
Yes, sir, I can see the size.
So tau is actually A1 over A naught, which is a time constant, basically in second. And Ks is actually B naught over A naught, which is a DC gain. Okay? So the solution to this complete response consists of two parts. The first one is the natural response or homogeneous solution. So basically that you force, basically that you're forcing function set equal to 0. So what it means is that you have an equation, the differential equation just now, that you have Ks f of t equal to 0. So you have tau dxn of t over dt plus xn of t equal to 0. Or it can be written as the derivative of x of n of t over dt is equal to minus xn of t over tau. So therefore, the solution is given by this equation. So x of n of t equal to alpha e minus t over tau. Right? Okay.
Yes, sir.
Okay.
So you just remember this. This you need to remember. The derivation of the formula, how to get from here to this, you don't need to worry about it. You just take the formula. Eh? Okay.
Okay, sir.
And the second part is that the forced response or particular solution. The solution of this equation, tau dxf of t over dt plus xf of t equal to ks f for t greater or equal to 0, which the forcing function f is equal to a constant for t equal to 0. Since the derivative terms become 0 in response to the constant f, thus the forced response is found to be this. So x of f of t equal to ksf for t is greater or equal to 0. Okay. So you need to remember those two formula. This formula and this formula. Okay.
Okay, sir.
So therefore, the complete response is actually the summation of nature response and force response. So therefore, the solution x of t is equal to xn of t plus xf of t, so equal to alpha e minus t over tau plus ks f. Or it can be written as alpha E minus T over tau plus X
X
of
infinity.
infinity. Okay?
Okay, sir.
So from here, you try to solve for the unknown constant of alpha. So what happened is that for for t equal to 0, at t equal to 0, so x of 0 is equal to alpha plus x at t equal to infinity. So therefore, alpha is equal to x of 0 minus x of infinity. So alpha is basically that the initial condition at t equal to 0 minus the final condition. So that is alpha. Do you know how to get this? Why alpha? Because e to the power of minus 0 is 1, or e to the power of 0 is 1, because at t equal to 0. Okay? So that's why you have alpha here. So alpha is equal to x of 0 minus x of infinity. So therefore, we can substitute alpha, this value of alpha into this equation. So therefore, you get x minus 0, x of 0 minus x of infinity times e minus t over tau plus x of infinity for t greater than or equal to 0. So in the transient analysis, we need to have this equation where x actually in this term. So what you need to do is that we need to find the initial condition, we need to find the final condition, we need to find the time constant. So there are three things that we need to find in the transient analysis. Okay? Initial condition, final condition, and time constant. Okay, initial condition, final condition, and time constant. Okay. Clear?
Yes, sir.
So for time constant, for capacitive circuit, is given by this formula. Tau is equal to RC. Okay. For time constant for inductive circuits, tau is equal to L over R. Okay. This T is stand for transient. Okay. How are we going to determine the time constant? Let's say you have this source-free RC circuits occurs when its DC source is suddenly disconnected. So basically that, let's say a DC source is being connected and you only have these circuits. So now, by KCL, you can write. So this is actually the node. So you have two currents going out from this node. So IC and IR. So IC plus IR is equal to 0. What is IR? IR is basically that the voltage across the resistor, so V over R. But the voltage across a capacitor is given by the formula of C dV dt. So you plug in the formula here. So you have V over R plus C dV over dt is equal to 0. Okay. So this is what you get. Then you rearrange the equation. So that's why you get tau is equal to RC. So the natural response of a circuit refers to the behavior in terms of voltage and current of the circuit itself, with no external source or source of excitation. So the time constant tau of a circuit is the time required for the response to decay by a factor of 1 over E or 36.8% of the initial value. Let's say the initial value is V naught. Okay, so the tau is basically that when you have the value of 0.38 of V naught. So this is the value of tau. When the voltage or current decay by 0.38 of the initial value. Right? So V decays faster for small tau and slower for large tau.
Oh.
So this is actually for tau is large, then it's slower. For tau is small, then it decays faster. Right? Because remember, e to the minus t over tau. Right? So large one, so basically that is smaller. A large tau, basically e to the power of large tau is getting smaller. So this one is decay faster when tau is smaller because it's a reciprocal of tau, 1 over tau. Okay. The key to working with a source RC circuit is finding this. Vt is equal to V naught E minus T over tau, where tau is equal to RC. So the initial voltage V naught, V at T equal to 0 is equal to V naught across the capacitor, and the time constant is T over tau is equal to RC. So just remember this when you want to solve the transient analysis. For RL, same type of circuit, but now you have an L instead of C. So you have a note here. Now you are this one, since we need the current, so we use the KVL, right? So we use the KVL. So voltage across the inductor plus the voltage across the resistor is equal to 0. What is the voltage across the inductor? It's L di over dt, and the voltage across the resistor is IR. So L di over dt plus IR is equal to 0. So therefore, di over I is equal to RL R over L dt. When you solve this equation, then you get I of t is equal to I naught E minus R t over L. So tau is equal to L over R. Betul? Yeah. So now you have the I of t is I naught E minus t over tau, and tau is L over R. So for the time constant, for the RL circuit, is that tau is a circuit of the time required for the response to decay by a factor of macam tadi juga 1 over E or 36.8% of the initial voltage. So I of t decays faster for small tau and slower for large tau. So the general form is basically very similar to the RC source-free circuit. So just like the only difference is that for inductor is current, for the capacitor is the voltage. Itu je. And also, you have this formula. So IT is equal to I naught E to the minus T over tau, where tau is L over R. So the initial voltage I at T equal to 0 is equal to I naught, and tau is equal to L over R. So this is basically for RL, and this for RC. So the curve is almost the same. The only difference is that for inductor is the current, for the capacitor is the voltage. Okay? And the formula also looks the same. Right? Set this only. And the time constant. Right? L over R, this one is RC. Okay. Clear?
Yes, sir.
Clear,
Example.
sir.
Same example just now. Similar example, not the same, because the value are different. Okay. So at t less than 0, the circuit shown is at a steady state. The example previously was an inductor. This one is capacitor. The switch is changed as shown at t equal to 0. You are given Vs1 equal to 35 volts, Vs2 equal to 130 volts, the capacitor 11 microfarad, R1 70 kilo ohm, R2 is 7 kilo ohm, R3 is 23 kilo ohm. So determine at t equal to 0 by 0 plus the initial current through the R3 just after the switch is changed. And second, B, determine the time constant of the circuit for time t greater than 0. So you need to find the initial condition, and also you need to find the time constant, the tau. Tau is basically RC for the RC circuit. Right? But what is R in this case? You have to find the equivalent value, the equivalent, the R equivalent, not just take the one R value. It's an equivalent value. The R equivalent. So for the part 1, so you have to draw, for part A, you have to redraw the circuits. Okay. What happens to the capacitor at the DC is an open circuit. So now you draw the open circuit for the capacitor. So in this case, when this open circuit, basically that here there is no current flowing. So IR1 at 0 minus is usually equal to IR2 at 0 minus is equal to 0 because there is no current flowing. Okay. Because capacitor is behaving as an open circuit. Therefore, this KVL you can write as Vs1 minus the voltage across the R1 plus the voltage minus the voltage across the capacitor minus the voltage across the R2 plus or minus Vs2. Or you can write or the other way around, which is minus Vs1 plus voltage across R1 plus voltage across the capacitor plus the voltage across R2 plus Vs2 is equal to 0. So rearrange the equation. You have voltage across the capacitor at t equal to 0 minus is equal to Vs1 minus Vs2. So equal to 35 minus 130, so equal to minus 95 volts. Clear?
Clear, sir.
Okay.
Yes, sir.
So at t equal to 0 plus, remember that the voltage across the capacitor cannot change instantaneously. So that VC 0 plus is equal to VC of 0 minus, so equal to minus 95 volts. Right? So whatever it is, you have to draw the first. when t equal to 0 plus. So basically you have this loop, right?
Alright, sir.
So therefore you have this loop, right? You have this. So PS2 minus IR2 minus VC0 plus minus
IR3.
IR3 equal to 0, or the other way around, minus VS2 plus IR2 0 plus R2 plus VC 0 plus IR3 0 plus times R3 equal to 0. So it's just the K. So since IR2 is equal to IR3 because it's the same current flowing, so therefore we can rewrite the equation as minus VS2 plus IR3 R2 minus V0 plus I3 0 plus R3 equal to 0. So rearrange the equation. R2 plus R3 times IR3 0 plus is equal to VS2 plus VC 0 plus. Therefore, IR3 0 plus is equal to VS2 plus VC 0 plus over R2 plus R3. You substitute the value which is given previously. So therefore, you get 1.167 milliamps for the current is 1.167 milliamps. Okay. That is part 1. For part B, you need a time constant. To RT, this, the transient. So you have this circuit. So what is RT? RT is basically that is in series, is connected in series because this one is connected. So basically that you have R2, you have capacitor, and you have the R3 are all in series. So basically R2 and R3 are in series. So RT is equal to R2 plus R3. So is 30, tau is equal to 30 kilo ohms multiplied by 11 microfarad. Tau is equal to 0.
Sir, sorry sir,
33.
your voice isn't clear.
Okay, dengar tak?
Tak clear sir.
Dengar tak?
Kurang clear sir.
Dengar tu, tapi dia
Kurang clear.
Tadi ada lekat-lekat sikit.
Okay. Tapi you apa ni you clear nampak the apa ni the equation, right?
nampak tu.
Question nampak sir.
Nampak saya equation.
So basically that for the RT is the R equivalent for these circuits. So because R2 basically they're in series with R3. So you have this. So now, how are we going to solve the first order transient response? So this is the step that you need to follow in order to solve the transient. First step, solve for the steady state response of the circuits. So what you need to do is that you need to find the initial condition and also the final condition. This first step, right? Second step, you need to identify the initial condition whether is this or this. This is actually for capacitor. This is for inductor, right? Then finally, you write the equation, the differential equation for t is equal to 0 plus. So xt here is that it's either for capacitor is voltage or for the inductor is the current. Then you reduce the circuit to Thevenin or Norton equivalent form with the energy source is treated as a load. Then you reduce the equation to the standard form. So basically that you reduce to this equation. For step, you calculate the tau. Calculate for tau. Okay. For capacitive circuit, this is the formula. For inductive circuit, this is the formula. Okay. Then you write the equation because this one is from step 1. Okay. This also from step 1. This from step 1. This one, tau, is from step 4. So this is your final equation that you write. Example. Determine the expression for the capacitor voltage in the circuit given. So Vc of t equal to 0 is given this. R is given that. Capacitor 470 and Vb is 12 volts. So now basically that you need to find the formula. So step 1, you find a steady state response for the initial condition. This is the initial condition. This for t equal to 0 minus. What happened to t equal to 0 minus? This is given. 5 volt. So VCT less than 0 or equal to VC0 minus equal to 5 volt. Clear?
Yes, sir.
Okay.
Yes, sir.
Second part, we need to find
Yes,
the
sir.
VC infinity. So when the switch has been closed for a long time, the capacitor current becomes 0. And the capacitor acts an open circuit. So therefore, VC infinity is equal to VB equal to 12 volts. Initial condition. By the virtue of continuity of capacitor voltage, therefore, VC0 plus is equal to VC0 minus equal to 5 volt. Step 3. Write the differential equation. So now we want to write the equation, the differential equation. So now we need to write the, what do you call it, this loop. So you have VB minus R times I minus the voltage of the capacitor is equal to 0. Where I of t equal to ICT equal to C dVt over dt. So for plus RC dVct over dt plus Vc of t equal to 0. So RC dVct over dt plus Vct is equal to Vb. Then this is this. So tau is the RC, and Ks f of t is equal to this part, and Vb. So now we have to find tau. Tau is RC. Whereas R is 1K C is 470 microfarad. So it's equal to 0.47. And Ks equal to 1 because Ft is equal to Vb. Yeah? So Ft is really the input. This is the source. So now we can plug in the value into the equation here. So x of t is equal to x of infinity plus x of 0 minus x of infinity e minus e to the power of minus t over tau. So therefore, since this is a capacitor, we need to write in Vc. So we have Vct equal to Vc infinity plus Vc 0 minus Vc infinity times e minus t over tau. So Vc infinity is 12. Vc of 0 is 5 from our calculation just now. And tau is 0.47. So we have this as the answer. Vc of t is equal to 12 minus 7e minus t over 0.47. Okay. Clear?
Yes, sir.
Clear, sir.
Clear, sir.
Okay. Now, exercise number 1. Determine Vc, Vx, and I/O for t greater than 0. Assume that Vc of 0 is equal to 45 volts. So we need to find the Vc here. And we need to find the Vx and we need to find the I/O. Boleh? Boleh cuba?
Tak, sir.
Ha?
Tak boleh, sir.
Tak boleh. Kita tak bagi solution pun. Kita bagi itu je. Tak boleh.
Tak, sir.
Kita ada berapa slide lagi? Okay, kejap saya tengok. 37, 38. Alah. Wah. Sekejap Kita pergi dekat. Nampak tak? Nampak slide?
Tak, sir.
Ha?
Tak nampak,
Keluar,
sir.
sir.
Nampak?
sir.
Sekejap. Kita ada 2 slide lagi. Okay, saya share balik. Nampak? Nampak tak?
Nampak.
Nampak, sir. Nampak.
Okay, nampak, sir.
Nampak tu.
So how are we going to find this? What is tau? RC, okay? What is R? R equivalent. For these circuits. What is R equivalent? Equal to
12, sir.
parallel with 6 plus 8.
One,
Plus always 6 for
12 parallel with many?
4, sir.
Huh?
4.
4. 4 plus
12.
8,
12 sir.
12.
12.
So
Yes, sir.
RT is 12. What is C?
0.0, 0.3.
RT 1/3. So basically
0.3
tau is equal to 12
times
times
1/3.
1/3. So it's equal to
4.
4. Okay. Equal to 4 seconds. Okay. What is the formula just now? V of CT is equal to VC of infinity, what, plus or minus of 0 minus V of infinity times E to the minus T over
Over tau.
T over tau. Minus T over tau.
tau. Right? What is VC infinity in this case?
It is 45 volts, sir. Minute.
What happened to the voltage? What happened to the charge in the capacitor at T equal to infinity? Is discharged, right? Totally discharged, equal to 0, right?
No, sir.
So when charge is equal to 0, what is the voltage across this capacitor? 0, right?
0, sir.
Kosong, yes sir. Yes sir, kosong.
So this is 0. This is 0. What is VC of 0?
45, sir.
45. So you have
45, sir.
45. So now you have 0 plus 45 minus 0 times e to the minus t. What is tau?
4, sir.
4.
4.
So you have 45. You have 45 times e to the minus t over 4. 1 over 4 is what?
0.2.
0.25. So that's how you get it. Okay.
Okay sir.
So what is Vx? So voltage across this. So Vx is equal to what? Vc plus V over V across 8 ohm resistor, right? So this voltage plus across this voltage, right? At. So it's equal Vx, right?
Right, sir.
Oh, tak dengar, sir.
Right? Later what? Try to find the Vx. Play what?
That's it.
Play that.
Cannot, sir.
Ha?
Cannot, sir.
Boleh buat tak?
Tak dapat sir.
Tak dapat. Okay. At t is equal to 0,
Ya.
this is 45, right?
Okay.
45 at v equal to 0. Okay. Now, what is the combined register value here? Is
4 sir.
4.
Four.
Okay. This is 8. Okay. Voltage divider
Oh.
here is considered as 45. So what is the voltage divider?
Doblar.
Eh?
2 1 2 sifar 1.
So
2
45 and 4,
40,
right? There
45 and 4.
is 8 and 4. So basically is 2 to 1,
2 to
right?
1. Nisbah.
So 45
3, 15.
divided by 3 is 15. So here is 15. Here is 30.
30.
So here is 15. Okay. Here.
Ah,
So
clear sir.
now you have Vx of t is equal to Vx of infinity plus Vx of 0 minus
Minus
Vx
Vx
infinity
infinity.
e to the minus e to the minus t over tau.
Tau.
Tau is the same. Vx infinity is what?
0. 0 sir.
0. Because this 0 here. Vx of 0 is 15.
15. 15. Yes sir.
And that is 0. So you get 15
15
e to the
exponent.
minus 0.25 t.
Oh, Akbar.
Okay.
Okay. Okay.
So now I not. How?
I note.
Uh, how? Now you have a circuit like you have right? Right?
Yes
So
sir.
this is what? 4.
Yes sir.
This is 8. This is 45. So what is I? Use the
Use the Ohm law.
you use the KVL.
Okay. KVL sorry.
Okay. Try. What do you get? Basically, you get 45 plus I naught times 8 plus
15.
what 4 times I naught is equal to 0. So
Betul
I
sir.
naught is equal to minus 45 divided by
By 12.
12. So basically this is what we call it 45 e to the minus 0.25 t. Yeah, I just make it simple, easy. So
Okay
basically
sir.
that. Eh?
Okay.
So basically, this is actually 45. If I want to write it full, e to the minus 0.25 t. Here, VC. Okay. So now, minus 45 divided by 12.
5.
Minus 3.75.
5. Ya Allah.
That's how you solve. Okay?
Yes, sir.
Okay, sir.
Clear?
Yes, sir.
Clear, sir. Allah Akbar.
Memang kena tulis penuh ataupun boleh tulis pendek macam tu je, sir. 45 tu.
You have to remember your nodal analysis, your current, your voltage divider. You have to remember your R equivalent, how to calculate. All actually combine, and you use how to do the analysis.
Okay, sir.
A simple circuit, but you use a lot of the rules and the formula that we learned in previous chapter. This one, the switch in circuit below is open at t equal to 0. Find Vt for t greater than 0 and Wc of 0. So you need to remember the equation. The equation is what? Vc of t is equal to Vc of infinity plus Vc of 0
VC 0
minus
minus
Vc of
VC
infinity
of
times e to the minus t
t
over tau.
over tau.
Okay? So basically that originally t is the switch is closed. So when it's closed, what happened to this? It's an open circuit. Okay? An open circuit. So V is basically the voltage across this capacitor, this resistor. So at T, okay, less than 0, so you draw the circuit. So you have that. You have 6 here, 4 here, and 12 here. So what is the voltage across here? Voltage divider. 12 and 4, what is this?
3.
3, sir.
3, sir.
So you have 6 and 3. So 2 to 1.
2 to
So
1,
this
yes,
is 24. 24. So basically 8.
8.
So V is so V at 0 minus is equal to 8, right? 8 volts. Okay. So when this is open, so what is the voltage across here? At T infinity.
0,
When
sir.
this is fully discharged, what happens to the voltage?
0.
It's
0, sir.
0. So you have V of C is equal to 0 plus 8 minus 0 e to the minus t over tau. What is tau?
Tau is 3.
Equivalent
1 over 6 times 1 over 6 plus 1 over 6 times 6 over
What is tau?
1 over 6
9. 1 over times 9,
What is tau?
1 over 6 times no.
12 parallel with, okay, let us draw. At t is infinity. Basically that you have the circuit of this. And you have the capacitor here, right? Okay.
Yes, sir.
What is T? What is R? 12 parallel with 4 is
3.
3.
3 ohm.
RT is that. So tau is equal to RT times C. So tau is equal to 3 times 1 over 6 equal to
1 over 2.
1 over 2.
2.
So
0.5.
this is equal to 8 e to the minus t over 0.5. So
5.
it's equal to 8 times e to the minus 2 t.
Oh.
6 tu memang tak dikira ya, sir.
Huh?
6 register 6 ohm tu.
This one. This one.
Nampak dia dah buka
Because dia
kan.
open. Bila open, there is no
No.
Masuk dalam tu.
there is a disconnected from the circuits.
Oh, okay. Faham.
So the effective circuit is only this part. This part.
Okay.
40
Okay,
infinity. So that's why the R equivalent is only looking from here. Basically, you take out the capacitor and you calculate for R infinity, RT there. Okay?
Okay, sir.
Okay. Then need to find the VC of at 0. What is the formula for VC? WC equal to 1/2 C what? C square. So
CV kat.
formula from last week.
Oh, Allah, ni ingat balik ni. Kena ingat balik ni. Kena tengok balik.
So at T is equal to 0. So basically T is 8. So 8 square is 64. 64 times 1 over 6. So 64 divided by 6. Divide by
1, 0.
dapat tak 5.33? Dapat tak?
Berapa je?
Cuba apa ni?
Dapat, sir. 5.33.
Basically it's the half times C
Betul je.
V square. So V is, this one is basically 1/2 times 1
1
over
over
6
6
times
dengan X square.
8 square. Dapat?
Dapat saya.
64 divided by 2 divided by 6. Dapat?
Dapat saya.
Okay.
Dapat sir.
That is the example of how you do the transient analysis. Another example. For the circuit, find IT for t greater than 0. So at t equal to 0, at t less than 0, the switch is closed, right?
Right.
So
Yes, sir.
the switch is closed, so therefore that you have the current flowing. So basically that this is charging. Okay.
Okay, sir.
Can you do this for your exercise? Boleh?
Can try it.
Boleh sir. Boleh.
Boleh.
InsyaAllah saya cuba, sir.
So basically that I leave this for you to try and on your own whether you get this answer or not.
Alright, sir.
Okay. I want you to try on your own. I'm not going to teach you this exercise.
Okay,
Okay.
sir. Okay, sir.
I think this is the last exercise. I think the last slide, right?
Yes.
So I leave this for you to do on your own. Just follow what I have taught for in the example exercise 1 and 2. So you do this, okay? So, any question?
No, sir.
No question.
No,